Hello, and welcome back to the AI Decision Makers Summit. My name is Brittany Sullivan with Argyle, and it's great to have everyone joining us today. A couple of notes before I turn things over to our esteemed speaker. First, a quick reminder to stop by our sponsors' virtual booths at any time during today's event and for the following week. Our partners are committed to providing you with valuable content and a great overall experience. At any time during today's event, you can visit their virtual booths from the main agenda page, which includes complimentary materials, information, and meet and greet opportunities. To ask questions throughout the session, simply type into the Q&A chat and we will address your questions at the end of the session. Now, without further delay, I would like to introduce our speaker, Stephen Hillian, Senior Vice President of Data and AI at Astronomer. We're excited to have Stephen with us for their thought leadership presentation titled, How the World's Best Machine Learning Teams Get AI into Production. Welcome, Stephen, and over to you.
Great, thanks, Brittany. Happy to be here and to talk a little bit about, well, as you say, how the world's best machine learning teams get AI into production. Actually, maybe let me cheat here a little bit. I'm going to go to this this chat bot that my team created. We called it Ask Astro. I'll explain a little bit more about what this is later in my presentation, but you can think of it as a fairly standard conversational AI assistant that uses data about the platform that we've produced, which is based on the Apache Airflow project for data engineers. And we're ingesting data from a variety of different sources so that you can ask questions about, well, our platform and about Airflow. And I thought rather than deliver a presentation myself, well, I can just get the chatbot to do it. So I typed in the title of the presentation and here we go. Turns out the answer to how you get AI into production is that you use tools and platforms like Apache Airflow. Maybe that's a little self-serving, but I think it does make an important point, which is that delivering AI requires delivering AI in production. You can't just treat this as sort of a research project. And to get AI into production and machine learning in general, you need an MLOps platform. And I'm going to talk about some of the requirements for that platform today and why Airflow is so widely used and accepted in that context. But I think I'll deliver it myself rather than rely on AI to do it. Let me give a brief overview of some observations I've been making over the last year or so as we at Astronomer have focused on how Airflow, and I'll talk more about Airflow in a second, is relevant for AI machine learning. I think the first observation is kind of an obvious one, is that almost every organization that has data, which is every organization, has been affected by this revolution in generative AI and large language models in particular. And people, well, like myself, who run data teams and run machine learning teams, are being asked to take advantage of this new technology almost as a requirement in itself, just like do something. And that often leads people into a little bit of a quandary. It's like, how can I make use of this technology, but do it in such a way that it actually contributes to my business, it actually does something meaningful rather than sort of hit a checkbox. And then it turns out it's not so easy to do. These generative models are very unwieldy. They don't always behave like you think they're going to. So that's a big challenge. And I found time and time again that I'm talking to teams who either don't know what to do or they know exactly what to do, but are finding it pretty difficult to actually turn these things into something that's operational. I think the other observation that I'll make is that traditional machine learning, classical machine learning, what do I mean by that? I guess anything that is not using one of these generative AI models, whether it's sort of classical regressions and classifications and dimensionality reduction, or whether it's other forms of neural networks and deep learning, that traditional ML is not going anywhere. It's almost amusing to me when I talk to data leaders or I'm interviewing candidates for machine learning roles. People are almost embarrassed to admit that, well, we didn't actually use large language models to do this. We just used XGBoost, or we just used a linear regression. And I don't think people should be embarrassed, because that stuff is not going away. And it's also very hard to do. So I want to make sure that I expand the net a little bit larger to talk about machine learning and AI generally, not just about generative AI. So let me talk about what the challenges are here. Why is it hard to get machine learning actually operational as opposed to just something that's running in someone's notebook? Well, that's actually the first issue, which is that often that development is very isolated. You have data scientists who really are developing things in a one-off environment, whether that's a Jupyter notebook or at the command line or in a third-party application that's separated from sort of operational data pipelines. That leads then to another problem, which is that there aren't a set of standards that have been deployed across different machine learning teams. I think software engineers pretty good at enforcing standards and having a routine way of doing this and having a well-defined SDLC and a CI/CD process. That's less true for data engineers, but I think data engineers are getting there. And I think now there's sort of standard processes around how you build pipelines and the concept of data meshes and so on. In the machine learning world, it's still the most common phrase I hear from data leaders, which is it's the Wild West. And it's not just that there's a lack of standardization, it's also that you have this overwhelming technology landscape. I mean, you see these eye charts of technologies that people have to use, and people are really overwhelmed by how to integrate all of those together. So there's a lack of best practices, but there's also a lack of coordination around the technologies themselves. You have literally dozens, if not hundreds, of open source libraries and third-party commercial applications that data scientists feel free to use and machine learning engineers find difficult to deploy into production. And then, of course, you've got the vicissitudes of how to operationalize these things in a way that is ethical and legal and compliant. So those compliance hurdles, the sort of the day two operational aspects of running these pipelines can be as overwhelming for machine learning as it is for other ops, DevOps focused teams, but perhaps even more so because of the sort of somewhat unpredictable nature of machine learning models, especially in the generative AI world. So those are the challenges. Looked at another way, there's just a hell of a lot of things that you have to do, that you have to get right in order to operationalize a machine learning pipeline. There's all the data prep. In a sense, you are relying on the upstream data workers, the data engineers, to deliver you clean data sets that you can really use reliably and reproducibly in models. Then you have to take those and do your own form of data prep in the form of feature generation and generate feature stores that can be relied on to deliver features quickly and reliably and reproducibly. And that can be shared and avoiding duplication of effort. Feature generation is a huge problem before you even get to the process of experimenting and training models. In some sense, the model training, once you've got those feature set, is relatively easy, though of course you have challenges there related to the amount of compute that you have and champion challenges and so on. And as you get into truly operational models, you need to make sure that those are versioned and that you're monitoring them continuously for error and for drift, and that you can replace those over time as necessary with retrained models or even completely different model forms. So that whole process, to the point where you can get the model in production, is very multifaceted and very complex. And then layered on top of that, you have all of the requirements around making sure that you can scale this out to many models, many teams, many pipelines. You can do that reliably. I mean, of course, things fail. And you need to be able to retry those if things are going wrong. You then need to have some sort of auditability around that and governance, so that you have transparency into the way that those pipelines are running, and you have lineage, and you know where your data is coming from, which data set produced by which person produced this prediction. All of that has to be orchestrated together. People often think of orchestration, data orchestration, as sort of a separate checkbox on this list. I really think of it as being the checkbox to rule them all, the checkbox that if you get orchestration right, if you can coordinate all of these different activities, all of the other things essentially come for free. And that may sound a little glib, but I think if you have a well-built orchestration framework that can do all of your data engineering, your feature stores, and so on, then you kind of solve the problem. And that's why we believe a framework for orchestration is the framework for doing MLOps. And I'm going to spend the rest of my talk talking about really what I mean by that. In a sense, what I'm saying is that machine learning is a form of data engineering. If you look at that list that I was just creating there, almost everything that you have to do there around scalability and reproducibility and handling compute and repeatably running model training, developing new data sets for features and so on, they're all the same problems that data engineers face. So if there's a single insight that I'm trying to get across here in the remainder of my talk, it's that machine learning engineering, ML ops, equals data engineering. Now, I think that's in a sense a controversial point, because as a machine learning engineer, I might say, well, no, it's much more complicated than that, right? Data engineers don't have to deal with the unreliability of predictive models in terms of errors and drift over time. But that's actually not true. New data sets that are being produced by data engineers are subject to all of the QA procedures and requirements that you need for machine learning models as well. In a sense, everything that the data engineer, machine learning engineer can be reduced to data in, data out, done in a way that's reliable and scalable, relying on different compute and different libraries and different technologies. I do acknowledge that there are some concrete differences. That's not what I'm going to focus on today. I want to make the point that if you can solve the world of problems that a data engineer has to face, you should apply those same solutions to the world of the machine learning engineer, and that's going to get you 99% of the way there, at least in our experience. So let's focus a little bit on data pipelines and the work of the data engineer, because they really power modern business. The way that businesses get information out, whether it's to users or to executives, to customers, to other data teams, to machine learning folks, the way that you get that out is by managing complex data pipelines. And most organizations, most modern organizations now have, whether they know it or not, have thousands, if not tens of thousands of data pipelines that power their business, that sit behind end user applications, that sit behind reports, that sit behind dashboards, that sit behind machine learning models. So let's be concrete here, right? Lyft, for example, the organization at Lyft has thousands upon thousands of pipelines that are used for every route that a driver drives, every offer that is made to an end user, every price that is quoted. Every single interaction of their application is powered by data sets and by machine learning models, is powered by pipelines that all have to be orchestrated and organized together. Walmart, their supply chain is dependent on a supply chain of data. The delivery of stock in time for the holidays has to be coordinated, and that is all coordinated through data, and that's all coordinated through an immense complexity of data pipelines produced by hundreds of data engineering teams. You look like an organization like FanDuel, for example. They use predictive analytics and traditional analytics to determine the right odds for sport betting, the right metrics that they use to make sure that they're geared up to handle the new NFL season when the traffic to their applications increases enormously. So those organizations have many different pipelines. How are those managed? They're all managed through Airflow. Everything that I just mentioned to you, all of those interactions at Lyft, all of those supply chains for a big retailer like Walmart, all of the predictive analytics and dashboards and operational decision-making for FanDuel are all powered by Apache Airflow, the open source project. This slide, it's amazing. This slide is just a few months old. We're now down to up to 30 million downloads a month for Apache Airflow. It is enormously popular. It's used by almost every organization out there for some, in many cases, all of the data pipelines that drive the sort of applications that I'm talking about. Astronomer is the commercial developer for Airflow. We produce a cloud platform for running Airflow deployments to power your pipelines. So Apache Airflow is the way that modern organizations run these data pipelines. And my argument then is that those pipelines can be machine learning pipelines as much as they can be data engineering pipelines. And in fact, if you look at all of the organizations that are using Airflow, these are all Astronomer customers here. And I mentioned a few of those like FanDuel and Walmart. They use Apache Airflow for their data pipelines, and those include their machine learning pipelines. By our reckoning, there are tens of thousands, of organizations that use Apache Airflow for data engineering, and about 30% of those organizations use them also for managing their machine learning pipelines. So in a sense, that's my point, is how do the world's best machine learning teams, like those I just mentioned at Lyft and Faddle, how do they get machine learning pipelines into operation? They use a data orchestration platform. They use Airflow. Okay, let me give some specific examples. I've already mentioned FanDuel, right? So the way that they manage all of their operational analytics is by running these pipelines. And they have 120 data engineering teams. So think of the complexity there. Each of those data engineering and machine learning engineering teams are building new pipelines, and all of those have to be coordinated together. You'd never have plumbing for a large building and not have that plumbing all integrated together. And it's the same for your data pipelines. And so using Airflow, and Astro, the platform that Astronomer produces, they can manage all of the coordination of that and do it in a very cost-effective way. They're literally running hundreds of thousands of tasks every month that produce these new data sets and these analytics, and they do that in a very cost-effective, reliable way using that orchestration platform. My favorite example actually is the organization Laurel. I want to just give you an example specifically of how they manage their machine learning pipeline. So how is it that organizations like Laurel actually do this, right? So what does Laurel do? They actually use AI-based models in order to predict for a lawyer or an accountant what they're doing on a minute-by-minute basis. You probably know that lawyers and other professional services have to produce timesheets at the end of every day that track literally every 5 minutes what it is that they're doing so that they can bill their clients. That's incredibly tedious. It is exactly the sort of work that you want your computer to do. It knows in some sense what you're doing. And so they have these predictive models that say, based on the windows that you're using, what you're typing, the mouse actions and so on, I can predict that you're working on a client brief or you're on a call with a defendant or whatever it might be. So they build these predictive models. The conditions under which the lawyers are working can change, the projects that they work on, different trends. So those models have to be refreshed literally every day. And they're constantly monitoring those models. They produce hundreds of models that are configured for specific clients and for specific types of work. So imagine the complexity where your business completely depends on having those models up to date and fresh. If those machine learning pipelines go down, then Laurel loses track of what their users are doing, and they get inaccurate predictions, and very, very quickly users get irritated. So it's incredibly important for them to have up-to-date, fresh models that are refreshed daily, if not hourly. So how do they do this? Well, they go through all those steps that I was just mentioning. They do the data prep in the ETL using Astro and Airflow. That's a very classic use of the Airflow platform. But they also do the model training with that same platform. They manage all of the compute with that in their Kubernetes cluster. They do all of the model training and versioning by running that in Airflow and then storing the results out to S3 and keeping track of that in a Postgres database. They then have separate Airflow pipelines that monitor the accuracy of those models and then trigger a new model training if ever it dips below a certain threshold. They also have most of those models that they're doing to do the predictions for lawyers are classical models, but they also have to summarize what the client has done at the end of the day in a written document, and they use large language models for doing that. And those are fine-tuned large language models. Guess how they're doing the fine-tuning and how they're running all of those? That's also with Airflow. All of that is done in a way that essentially runs lights out, but with complete transparency, thanks to using that framework. Now I really want to lift the lid, however, on exactly how they do that. So if Laurel is able to do all of these steps using Airflow, what does that actually look like? Well, I'm going to use Ask Astro, the application that I was just showing you, as an illustration of how to do that. And I actually want to encourage anybody out there who has a team that is working with machine learning models and large language models in particular to actually take a look at what we're doing in Ask Astro. I'm going to share the code with you later, and you can share that with your teams and see if that actually makes their lives easier. My claim is that it will. So I talked about Ask Astro. It's a conversational AI assistant that allows you to type in questions about Airflow and data engineering and about our platform. And then it'll spit out an answer that hopefully is relevant. And then you can continue that conversation. So a very classic sort of conversational assistant. This uses an approach that probably many of you on this call, on this conference are familiar with, which is retrieval augmented generation. It's a particular type of use of large language models that I think a lot of teams use as sort of their first stop, their first foray into the use of large language models, where you can use an external large language model like one from OpenAI or from Cohere or any of the other big LLM suppliers, but then you can essentially augment that with your own specific proprietary data, perhaps your internal documentation or public documentation or whatever it might be, to essentially prompt the large language model to give more relevant questions. So that's exactly what we've built with Ask Astro. You can go to ask.astronomer.io. You can also go to the Apache Airflow Slack community, and you can use our chat bot and our chat application there to ask these questions. It's already proven to be very popular. We get hundreds of questions a day. We get something between 70 and 80% thumbs up in terms of accuracy, which is about industry standard, if not slightly higher. So we're very pleased. But much more than offering a service, a conversational assistant, we did this because we wanted to have an example of how you can operationalize these large language models very straightforwardly. So we've open sourced all of the code that's behind Ask Astro. So if you go to the website, you can actually see all of that code, and it'll take you to the GitHub project where you can clone that and use it for yourself. So what actually is it doing behind the scenes? Well, at a high level, the way that the application works is it ingests all of the information that we have specific to how Airflow works. So these are documents that are stored in Markdown, Slack messages, information from Stack Overflow, GitHub issues, all of that documentation and intelligence that's been created by the community and by our documentation folks and by end users is ingested into a vector database. In this case, we use the one provided by Weaviate. And that whole process of ingesting and learning from that data and kicking off the large language models is managed by Airflow. So this is I've illustrated it here as a single pipeline. It's actually several pipelines, but just for simplicity, you can think of what we do is we go out onto the internet, we search through all of that public facing content from Stack Overflow, from the docs, from Slack and so on. We use the LangChain libraries to essentially do the data engineering, to split up those documents into manageable chunks, do the appropriate sort of tokenization. And then we call the OpenAI LLM service to its embedding model to turn those documents into vectors, into numerical vectors that represent the content of those documents. And we store that in the vector database Weaviate. And that now means that the Ask Astro application that I showed you before can call to that vector database and say, hey, here's a question. Please give me the most relevant documents that you've ingested. And then I can use that to prompt the large language model to give it the right answer. And so that's exactly how this answer was generated here. We actually found these documents that were relevant. We fed them into the large language model to say, hey, please answer this question, but use this information to answer it. And it generated this answer here. So that application, as I mentioned, if you go to, sorry, I don't want to show you my personal email. If you go to the Ask Astro site, you can see there a link to the GitHub application. So I really do encourage you to take a look at this. This is a way to build your own RAG-style application that runs in production lights out in a completely reliable and transparent way. We run this actually at fairly low cost on our platform. And so these data pipelines are running every night, ingesting the latest data, the latest conversations that are happening on these public sites to make sure that the answers that Ask Astro gives are relevant and accurate. So that's, in a sense, how my team has taken machine learning models and large language models and put them into production. And as I say, about 30% of all of the thousands of organizations out there that use Airflow also use it for managing these type of pipelines. Finally then, and I'll leave it open for questions in the last few minutes, but I just want to point out some of the things that we've learned here. First of all, that it's really important for the teams that use data engineering and machine learning pipelines to be united on a common platform. It makes absolutely no sense to have data pipelines that are used by data engineers for their data sets and data pipelines that are used for ML engineers for their models to be running on different platforms. They should really have a unified platform that allows them to standardize all of their practices across one common orchestrator. Also, managing the compute is very expensive, especially for these generative AI. As soon as you go into things like fine-tuning of these models, even if you're building those applications before, most of the world's largest producers of LLMs are also using Airflow to do all of the data engineering that powers those models. Amazon, for example, has many different applications of LLMs, and there's a general mandate to use Airflow to power those. So whether you're a user of LLMs or an actual producer of LLMs, you'll find that that orchestration platform applies, and it can actually manage your compute and do that in a cost-effective way. Perhaps the biggest lesson that we've learned is the importance of data lineage. If you're reading all of these documents from various sites, how do you know that the copyright is appropriate? How do you know that this prediction was produced by this data set created by this user? Well, you do that through a platform that tracks all of those pipelines from beginning to end. So that data lineage aspect is perhaps one of the biggest lessons that LLM teams are using, that you need to know where your predictions are coming from. And that's true for traditional machine learning as well. And then finally, as is always the case, there are a lot of different technologies that we're using here. I mentioned LangChain, inspector databases, different LLMs. We're actually using multiple LLM services for Ask Astro, and that's true in general for our customers. And so having one point that knows how to integrate all of these, a platform like Airflow comes with thousands of different integrations. So I think in general, my conclusion here, right, is to think of ML engineering at first approximation to be a type of data engineering, and to think about the standards and best practices that have been developed over the last 10 to 15 years by data engineering teams, and to realize that the same orchestration best practices that can be brought to bear on data engineering can also be brought to bear on machine learning engineering as well. Okay, thanks very much. I don't know if there are any questions. I'd be happy to answer those.
Yeah, excellent. Thank you so much, Stephen, for such an insightful presentation. We did have quite a few questions come through, so it looks like we have time to answer a couple of them. This first question asks, how can you ensure existing ML works successfully alongside new AI implementations?
Yes. Presumably the questioner means sort of traditional ML versus LLM. I think that in many cases, what you find is that you are executing the same types of tasks. So that checklist that I was showing you before still applies to these generative applications. In many cases, you may not be tuning a model, but you're certainly generating data and feeding those into models, and then you're monitoring the accuracy over those over time. And I think perhaps the biggest lesson that I've seen learned is that you need some framework for doing that. Because if you expect your data scientists to be developing their own model training code, or their own model testing code, or their own data engineering code, then you're going to get into a chaotic situation right from the beginning. So you want to create high-level abstractions or utilities that can perform those functions and have those shared across your team. So when I look at a team that I'm familiar with, some of the ones that I've mentioned, you see that they all tend to have built a framework on top of an orchestrator like Airflow, for example, that has some higher level primitives that are common to all of your machine learning pipelines, so that everybody is using the same methods and practices to do that. So I think that would be my suggestion, is that both traditional machine learning and machine learning with generative AI will end up performing the same types of functions, and you want some high-level primitives to handle those. And if you have a platform like Airflow to use as the basis of that, and the way that you can push those out to end users, then that makes it a little easier.
Excellent. Thank you. Looks like we have time for at least one last question. What would you say the biggest risks are that are associated with new ML or AI capabilities?
I think two things. One is knowing the provenance of your data. I went to an interesting meetup just a few weeks ago by Cohere, that they were talking about this problem and how they develop these pipelines so that they can track things like copyright and sensitivities around the data. I think the other one is just the risk from accuracy. So there's a lot of enthusiasm for using these models, but they are very non-deterministic in nature. And so you need to have mechanisms that check that the validity of the answers that you're creating is maintained at a certain level of quality. And so we actually have pipelines, and you can find this in this open source implementation, where we continuously run sets of test questions, and we can measure the quality of those outputs. And there are lots of new techniques that people are developing where you can have more powerful LLMs judge the quality of the LLMs that you are producing. That may be more expensive, but you only run it, say, once a day or once a week. So those sorts of methods for maintaining quality are really important. They're very hard to automate, is the thing that we've learned, but it's also essential to have them at least semi-automated with some sort of human intervention as well to guarantee ground truth quality. I think those are the things: monitoring quality and data lineage for provenance of data.
Excellent. Well, thank you so much again, Stephen, for such an insightful presentation. That is all the time we have for questions, but thank you again. And thank you everyone else who joined us today. This session, along with all of today's content, will be made available on demand following the event. Thank you again, Stephen.
You bet. Thanks.